In this video, I'll be discussing the one of the applications of junction diode, and that is that this junction diode can be used as rectifier. So, to be simplistic, I would like to say that we have different modes of different ways of rectifying the AC signal and converting into the direct signal. And we would like to discuss one by one ways of modes of using PN junction as rectifier. And to start with, if I have to define rectification, it's a process of converting AC into DC. And this process is referred as rectification. And if I have to go with the principle of this rectifier, its principle is basically that the PN junction that we are making use of, the junction diode, it conducts only when forward biased. It does not conduct when it is reverse biased. So it acts as a valve. I mean, this fact makes the junction diode to work as a rectifier. So here we will be discussing this what's called as half wave rectifier, diode as half wave rectifier. And to proceed on, the best thing is to go with the circuit diagram. What we have here is we have a transformer, and let's go with that. This is the primary coil of the transformer. Here we have the current, and then we have the secondary coil of the transformer, and we have a PN junction at one of its ends, and then here we will have the load RL. So at this point we'll be able to get our output. So this is RL. So to go with this, the AC signal to be rectified is fed to this primary coil of the transformer. The secondary coil is connected to the junction, right? That could be seen diode through a load resistance from this side, and the output signal is obtained here. Now the question is, how does this thing work? I mean, we have an AC signal, right? It has a positive half and it has the negative half. So when the positive half cycle of AC input signal flows through the primary coil, right? And induced EMF, I mean, there sets up an EMF in this secondary coil due to mutual induction, right? The direction of that induced EMF is such that the upper end of the secondary coil becomes positive, and the lower end becomes negative. I mean, since the upper end of the secondary coil is connected to the P region of this junction diode, so and the lower end is connected to the N region, can directly see this. This is connected to the end region of the junction diode. So the junction diode in this case is forward biased. So during positive half cycle of the input AC, we have forward biasing of the PN junction. Thus, the junction diode conducts and flows the current here in this case, right? The output voltage, which varies in accordance with the input half cycle, we would like to draw that in terms of graphical presentation. So the point is clear here that we have, for positive half cycle of this signal, the PN junction is forward biased. Now for negative side of this this signal, when this negative cycle of AC input flows through this primary coil, again an induced EMF is set up across this secondary coil due to mutual induction. Now the direction of this induced EMF is such that the upper end of the secondary coil becomes negative and the lower end of this coil becomes positive. So in the first case, it was positive and this was negative. In the second case, now this is negative and this is positive, right? So the junction diode in this case is reverse biased, because we are having negative terminal connected to the P side of this PN junction, and positive side is connected to the N junction. So hence this junction diode it does not conduct. Therefore, we get no output across the resistor, across the load resistance during the negative half cycle of the input. So the input and the corresponding output voltages, we can have a graphical representation of the output that's obtained here and the input that we have given to this PN junction, and no doubt this is called as half wave rectifier, because we could see that that we could only make PN junction conduct for the positive half cycle of this signal. So if we go with the input signal here in this case, suppose I have an input signal, okay, it will be like this, right? Okay, so this is my input, and corresponding to this, I want to plot. I would like to plot the output. Now, for this positive half cycle of AC, it conducts. Okay, so I would like to make dots here. And for this negative cycle, it does not conduct. Then again, it conducts, and the process goes on. So here we will have an output like this. So here we have zero output, then we have output, then we have output. So we can see that we have rectified the input signal, but we can understand that there is wastage of the negative half cycle of the input signal. So here we have rectified signal. So you can have this 0, then certainly this will be pi, then this will be 2 pi, and so on and so forth. And here if I choose this as current, and this I choose as omega t, right? And so here we have AC, and here we have DC output. Now the point is clear that only the half cycle or the full cycle of the AC signal is utilized, and therefore it has disadvantages like since the output signal is discontinuous. You can see it's a discontinuous signal, so the efficiency of half wave rectifier is small. So I should say the efficiency is small, right? And the output is not pure DC, right? Because it still has fluctuations in it. It still has the pulsating signal in it, pulsating DC, which contains AC components, or we also call them ripples, right? Now, if I have to write for the output DC voltage of this half wave rectifier, output DC voltage, and that voltage is defined as the product of mean load current times DC RL. Okay, so this is VDC is mean load current, so this is IDC that we have obtained times RL. So this will be my output voltage that we will obtain in this case. But we understand that for this half cycle, we have the mean value of current, and that mean value of current is calculated as that IDC. That IDC is what is that? That is I naught by pi. So we can say that VDC of the half wave rectified signal is I naught by pi times RL. So this will give us the measure of the output voltage of the output of the half wave rectified signal. Now, after this, we would like to go with full wave rectification, right? And for full wave rectification, so this PN junction can be used. It can also be used as full wave rectifier, right? So in this case, what we are doing is we are making use of two PN junctions, and we are making use of both the sides of the AC signal, right? The positive half is used, as well as the negative half is used. So in order to achieve that, in order to understand this condition, if we go with the diagram for the full wave rectifier, we have, in the similar fashion, we have a transformer, right? And here we have the signal. This is the primary coil of the transformer. Then we have the secondary coil of the transformer, right? And from here we have a PN junction like this, and from here we have another PN junction like this, and we have to obtain the output at the load resistance RL. So this I will call as D1, diode 1. This I will call as diode 2. Now, we can see from figure it's justified that we are making use of two PN junctions, right? So how to explain this kind of thing and what's going on? I mean, the AC input signal is fed to this primary coil of the transformer, and the P region of both the diodes D1 and D2 are connected to two ends of the secondary coil S. So this is our secondary coil, and this is our primary coil. And the load resistance RL, across which the output voltage is obtained, it's connected between the common point of N region of diodes, right? So it's commonly connected to both the diodes. And you can see the central taping of the secondary coil here, right? So this is center taped, and the end regions of both the p-n junctions are exactly connected. Now, to understand the working of this full wave rectifier, it must be very simple to understand. It must be very simple to express as well. So what happens is we have the AC signal. Suppose this is the AC signal that we are using. Now, when the positive half cycle of the input AC signal flows through this primary coil, an EMF induces in the secondary coil, and it is set up in the secondary coil due to the mutual induction that we talked about. So the direction of induced EMF is such that the upper end becomes positive and the lower end becomes negative. So for this case, D1 is going to conduct, and D2 is not going to conduct, because D1 will be forward biased and D2 will be reverse biased. So the output voltage, which varies in accordance with the input signal, is obtained across the load resistance RL here, right? So this is the point for now. For during negative half cycle of the input signal, what's going to happen now, that now D1 will certainly be reverse biased, and D2 will be forward biased. The current due to D2 flows through the circuit in the direction, right? So we can see the flow. I mean, in first case, this was plus and this was minus. This conducted, this did not. In the second case, this is reverse biased, and in this case, it is forward biased. And in both the cases, we are able to obtain the output at the load resistance, right? Now, since both the halves of the input wave are rectified, so that's why this junction diode is called as full wave rectifier. Now, certainly this rectifier has advantages because we are making use of both the cycles. I mean, so in full wave rectifier, output is continuous, right? We will have a continuous output in this case. So its efficiency is certainly more than that of half wave rectifier. However, the output is again fluctuating. It's not the same as we expect. So the presence of those pulsating DC signals, having these pulsations of some AC components in it, these things can be smoothed by making use of filter circuits. So for that we make use of filters, right? And if we talk about the output of this output DC voltage of full wave rectifier, so for that we have DC. So VDC, this is output DC voltage for this what's called as full wave rectifier. So it will be the product of mean load current times load resistance RL. Now, what's the value of mean load current in this case is twice I naught by pi times RL. So this will be VDC. So this way we have seen that how a half wave rectifier works and how a full wave rectifier works, and we could see the difference, and we could see that the efficiency of full wave rectifier is more than that of half wave rectifier, as the name suggests. So thus the DC voltage in case of full wave rectifier is twice the output of the that of the half wave rectifier. So it's 2 times that of whatever we have got for half wave rectifier. And one point must be noted here, that the frequency of the load current is equal to the frequency of the input supply for half-wave rectifier. On the other hand, the frequency of load current is twice the frequency of the input supply for the full wave rectifier. So with this, I would like to close down this video. I hope you understand, and if you have any suggestions, you can give me. I'm trying my best to do the best. So that's it. Have a nice time, all of you.